Oh hi, didn't see you there. If you're interested in engineering, this video will be right for you. Today we're going to learn about heat energy. Using this concept, we can calculate the power of a stove. Come on y'all, this is going to be hot. Alright, so heat is a form of energy. Energy is something intuitive, we consider it every day. There's mechanical energy like playing with the ball, lifting weights, even moving a car. Heat is the energy required to change the temperature of an object. It takes a lot more energy to melt an iceberg than it is to melt an ice cube. So using this concept, we're going to melt an ice cube, evaporate it, and see how long it takes. That will allow us to calculate the power of a stove. You're thinking like an engineer already. Alright, the experiment itself can't be any easier. All you have to do is boil some water and measure how long it takes. Okay, so here we have the equation for heat, which is Q, and it's mc delta T, or mass times heat capacity times your change in temperature. It's just an equation, we're gonna break it down. Alright, so first we have mass, it's how much stuff you have. The heat capacity is how much energy it takes to change that mass's temperature. And last is temperature, which we can either measure or we can think about using logic. Okay, so here's our situation with our stove. So we're gonna have a pan and the stove is gonna create some blue fire. You drop in the ice cube, which is a solid. It's gonna melt and it's gonna turn into a liquid and keep heating up, and eventually it will evaporate into a vapor or a gas. So using the logic of heat and energy transfer, we can calculate the power of the stove. Okay, so this is an experiment that you can try at home. The first part is pretty easy. So all you gotta do is measure the mass of a certain amount of water. If you have a scale, you can just do it something like that. Or using the concept of density, which is ratio mass over volume. So you can calculate the volume of the water and multiply it by the density. So if you want to be a little less precise, you can pretend that it's just a regular ice cube and then just do length times width times height. Or you can use this equation to find the volume. And whatever volume it is, you just multiply it by the density, which gives you the mass, which is the first term of this equation, cool. And the heat capacity is really easy because it's just 4.179 joules per gram degree Celsius. But be careful, because whatever unit you use for the mass and the density and the volume, you have to be consistent. Now we have the mass and the heat capacity. All we gotta do is think about this temperature term, but it's not as straightforward. Since this is a real experiment, there are going to be many errors involved. And I think the biggest error has to do with the heat transfer between the stove and the ice cube, because this equation assumes that the heat transfer is completely perfect. But I realized that if you put it on the stove, it's gonna get hot on the bottom, and then the heat will go through to the top. Meaning that the bottom could be melting, whereas the top is still solid, which means that will change how much energy it actually takes. Okay, we're gonna start by measuring the dimensions of the ice cube to calculate the volume. You can use the equation to find the volume and multiply it by the density, which is 1 gram per centimeter cube, to obtain the mass. Okay, so here we have liquid water, which is supposedly at 0 degrees Celsius since it just melted. And I'm gonna start the timer now. Alright y'all, so now we're going to discuss the different phases of matter. There's solid, liquid, and gas. Water exists as a solid when the temperature is at or below 0 degrees Celsius or 32 degrees Fahrenheit. Between 0 to 100 real quick degrees Celsius, water exists as a liquid. But with enough energy, we can boil this water and convert it into a vapor. If it reaches 100 degrees Celsius, it reaches its boiling point, and it needs a certain amount of energy in order to evaporate. This energy is called the heat of vaporization. So using this, we can simply add the heat of vaporization to our equation. Next, we multiply by the heat capacity of water. Now that we know the temperatures, which is 100 minus 0, we can add it to our equation. As you can see by the calculation, I got a total heat of 88,800 joules. And if you look at this equation, power is equal to heat per time. And I just divide by 58 seconds to get a total of 1,530 joules per second, or 1.5 kilowatts. Alright. According to reference.com, an average stovetop element uses 1,500 watts or 1.5 kilowatts per hour while it heats on medium or high. Since I got 1.53 kilowatts, that's a bit of an overestimate, but that's still under 2% error, which is pretty good. According to Wolfram, that's about 10% of the average power consumption per person in the USA in 2008. One calculation I thought of that may affect my results is the fact that the mass of the liquid changes as it evaporates. So I tried to turn it into a function of mass using calculus, but the error was really large. So maybe if there's a way to derive this equation, if you want to tell me, that'd be cool. Today we use equations to make a calculation in the real world. This is what engineers do every single day. If you think the concepts in this video were difficult, first of all, you can feel free to ask me any questions. But most of all, remember that practice makes perfect. You don't have to be smart to be an engineer, you just have to work hard. I hope to continue making engineering projects like these in the future. If you have any suggestions, you can leave a comment or subscribe to my channel. Do you agree or disagree? Feel free to say anything.